we're figuring out the electric field around things using Gauss's law last time. We are going to continue to use Gauss's law to figure out the electric field around various shapes. Please tell me, Zach, what is Gauss's law? I'm sorry, I can almost hear you. The closed surface integral
of the electric field dot product of the change in the area.
That's part of it. True. Dorfstetter? That's what the dot product would be. True.
Oh, it's the thingy. I know what it looks like.
What does it look like?
It's the eye, the little circle thingy, and a sub.
What is the eye with a circle thingy with a sub E called? Winter. The electric flux. What is the symbol called? The symbol. It's a capital Phi. So we have the electric flux is equal to the closed surface integral of the electric field with the dot product of dA. This is equal to what? Yuchik? That would be the left-hand side. I agree. We'll do stuff with that, but I want to know what this whole thing is equal to according to Gauss's law. I'm going to stop you. Potterella helps out.
Just EA.
Again, that's the left-hand side. We need the right-hand side. Sarah Jane Jones.
Q over E naught.
Q over E naught. What are we missing on Q over E naught? Miller.
Q in.
Q in. Q inside what? Catherine. Yeah.
Like the object.
Say again?
The object.
No, not inside the object. Inside what, Sierra?
The Gaussian surface.
The Gaussian surface, which you are going to draw every time you use Gauss's law. Good, I'm glad we reviewed. So here we go. We're going to figure out the electric field that exists everywhere around and inside a thin spherical uniformly charged shell. In other words, we have something that looks like this. A racquetball is a thin spherical shell. We're going to put a uniform charge on it of positive Q. So here we go. We have the shell. It looks like this. We know there is a positive charge located everywhere, uniformly throughout, only on the thin spherical shell. Let's start out with the electric field outside. Oh, we should give this, it has a radius of A. That radius of A, does it go to the inside of the thin spherical shell or the outside of the thin spherical shell? Mike? The radius A, does it go to the inside of the thin spherical shell or the outside of the thin spherical shell? The outside. Class is outside, correct?
Yes.
Yeah. Partially?
I would go with yes or no or partially, all as correct answers to my question. Doesn't matter because it's thin, right? By the fact that it's thin, this radius A could be to the inside, to the outside. It basically doesn't matter. That thickness of that shell is considered to be negligible compared to the size of A. So we're going to start out by figuring out the electric field equals question mark where R is greater than A. You should know the answer right now. We shouldn't have to derive it. You should be able to tell me what it is. Who could tell me what the answer is? Nick.
KQ over R squared.
You know this because?
Center of charge is just the center of
The center of charge is just this welt, but this is, the charge is all located out here. I agree if we figure out the center of charge, it would be right in the middle. But the charge is all located on the outside of this sphere. So how is it that we know that the electric field equals kq over r squared when r is greater than a? Vlad?
Is it because it's acting like a point charge?
Remember, we showed last time that as long as you are outside a sphere with uniform charge, it acts like a point charge. And if you are not asked to prove it, you do not have to. You can simply say it acts like a point charge. So the electric field is kq over r squared because it acts like a point charge. We did prove it last time. I'm not going to go through and prove it this time. Again, it's exactly the same as what we did last time for the one that was a solid sphere as opposed to a thin spherical shell. Now, what about figuring out the electric field where r is less than a? So if we're inside it, well, we need to use Gauss's law in order to prove this. So in order to use Gauss's law, what is our next step, Basil?
Get the red marker. And
Get the red marker out and draw
the Gaussian surface.
a Gaussian surface. I'm going to draw, it is again going to be spherical, and we're going to draw a Gaussian surface that looks like this. So there is our Gaussian surface. In this particular case, it is a sphere. So r is less than a. Okay? We start with this equation. However, I'm actually going to start on the right-hand side of this equation for right now. What is the charge inside the Gaussian surface? Located.
0.
0. Notice there is no charge inside that Gaussian surface. Considering the fact that the charge is equal to 0, we get that the closed surface integral E dot dA is equal to 0 divided by E naught. Therefore, the electric field is equal to 0. Go ahead.
When you treat the shell like a point charge, does that work even when r is just barely bigger than a?
If we're talking about r, as long as it is anything greater than a, we're fine. If r is less than a, and technically, I believe we could even say r is equal to a, greater than or equal to a. And as long as it's less than a, then we're going to get the electric field is equal to 0. So in this particular case, the electric field that exists around this thin spherical shell, the electric field as a function of r, is going to be equal to nothing until we get to a, and then the electric field looks like this.